Okay, so welcome everyone to the last day of the school. And well, we are happy to have Samir Murthy now, who is going to continue his lecture on microstate of supersymmetric a black hole in AdS. So please.
Okay, thank you very much. So let me begin as yesterday with a small recap, and then I'll pause for questions, and then we'll take it from there. So what have we learned so far? So we were studying n equal to 1 superconfirmed field theories in 4 dimensions, in particular n equal 4 superMUs, on S3 times S1 with some chemical potentials dual to certain charges. These charges included rotations, and therefore this is not a direct product. There's some twist involved. And we were studying the AdS CFT correspondence in this context, okay? And we were focusing on supersymmetric states, okay, so the supersymmetric sector of the correspondence. And in particular, yesterday we saw how to calculate the superconformal index of the field theory, okay? This is something like a Witten index with modifications as we discussed yesterday. This is dual to the supersymmetric partition function by the basic AdS CFT correspondence. That partition function has a sum over saddles, one of which is the black hole, and the action of the black hole we also calculated in the first lecture as a function of these chemical potentials. It goes as n square times 1 plus sigma plus tau cube divided by sigma tau. So it's some cubic divided by quadratic. So any questions about this? Wait, I want to say one more thing. And the main question, if you want, for today is that can we recover this black hole action, okay, from the superconformal index? So apologies for the fact that they're both conventional, and I didn't want to change that, but here I always try to write I graph, and here I try to give some curly things. All right. So the main question is, can we extract this on-shell action of the black hole from the superconformal index? Okay, so any questions about this? Okay. Then, sorry, it's still 1 o'clock and I'm still having my coffee. Okay. Was there a question?
You're muted.
Sorry, I couldn't hear you.
So, the question is whether the index is precisely the partition function.
Yes, the answer is yes, and I tried to explain this yesterday, that why this is the case. The answer is yes, that the superconformal index. So I'm not sure what exactly the question means. Can you spell it out? Are you worried about prefactors or something like this, or why at all they're equal? At what level? Can somebody, whoever asked the question?
Yes, maybe.
Sorry, it's Aviram here. No, sorry, I couldn't attend the lecture yesterday, so I just had a question whether up to cancellations and prefactors and everything, if they're equal.
Okay, good. If you didn't attend the lecture yesterday, let me just recap it in one sentence. The answer is yes. The superconformal index, as defined as a trace, okay, is precisely equal to the supersymmetric partition function. Oops, sorry, I don't know what happened. The supersymmetric partition function of the gravity, to which the supersymmetric black hole makes a contribution as a saddle point. So this was the subject of lecture 1. This was the subject. The fact that they're equal and what it is was the subject of lecture 2. Okay, that's so you can just take these as facts for today, and we can. Any other questions? Okay, sorry, I'm going to move on. All right. Sorry, I'm not sure the connection is okay. Can you hear me?
Yes.
Okay, thanks. Okay, so let's move on. Then we also saw an explicit expression for the superconfound index as an integral over the gauge holonomies of on the S1. So that's really the Cartan torus of the gauge group. Let's call it UN. It's an n-dimensional integral with some infinite products summarized by this elliptic gamma function. Okay, so there's some very explicit function here. This kappa n is some prefactor, essentially just some Pochhammer symbols. Okay, and the main question is from that expression that I just showed you, is this action contained in that expression? Okay, so it's I'm saying it in a deliberately vague manner because at least I was very confused about what exactly that question means. Okay, because there are different types of questions one can ask. So I'll try to unpack that a little bit. Okay, so at the first level, when we say once we've established that this index is equal to the supersymmetric partition function, you can go microcanonical on both sides. Okay, so if you go microcanonical in gravity, we've already spent the whole of the first lecture showing that the microcanonical transformation of the on-shell action of the black hole is the black hole entropy. Okay, those two are canonically conjugate. So on the gravitational side in the microcanonical ensemble, you literally get the black hole entropy. Remember the Ni, N1 and N2 in this expansion was J1 plus R over 2 and J2 plus R over 2. Okay, the things, the charges that commute with the supercharge. On the field theory side, the microcanonical objects are very simple. You just do a Fourier expansion of this index. Question? Somebody is not muted. Yeah.
Go ahead.
Sorry, question?
No, it was some background noise.
So you have some these Fourier coefficients, okay, which are a function of the charges and the gauge group. And the question of whether the index counts the black hole entropy in the microcanonical ensemble is simply this: is log of d of n, the absolute value of d of n, equal to the black hole entropy as a function of charges? This is a number, and that's a number as a function of n1 and 2. Okay, it's a very simple question. However, this question is still not so physically, so mathematically speaking, this is good, but physics-wise, there's a little bit of an issue because this n1 and 2 goes in any index from 1 to 3 up to infinity. And now you have to ask, in what regime of charges does the black hole solution make sense? Okay, and if you look at that, the right way to think about it in gravity is you take these charges, which we were discussing so far, we're discussing the capital one so far, and write them in gravitational units, divide them by n square. Those are the charges which a GR person would give you a solution in terms of. Okay, the black hole solutions are present in the first lecture are typically written in terms of these gravitational charges. Those are the natural ones. And if you want supergravity, then you should take to infinity. So that means G Newton goes to 0. Okay, and if you want a weakly coupled horizon, it means that as n goes to infinity, these gravitational charges should be fixed, so that you really have exactly what we call a black hole solution in weakly coupled gravity, right? Like the Schwarzschild solution. Okay, this limit I'm going to call the large n limit. This is called, not me, everyone calls this large n limit. I'm just making this very precise. Okay, in the context of black holes, n goes to infinity, and these gravitational charges are fixed. Okay, so now if you want to verify this expectation, okay, in this large n limit, I just want to give a sense for those of you who have not thought about this before as to why it's a difficult problem. Okay, suppose you want to calculate this on the computer. Okay, so these are some explicit functions. It's a 5-minute job to program this, and you can get the Fourier coefficients. That's not very difficult. What we are asking is you write, so let's say here's the index I1, you write I1, I2, I3, and so on. You make a list in the vertical direction. And then in the horizontal direction, you make a Fourier expansion. Okay. And now you're asking, you take the infinity in the vertical direction. You go to the central charge being infinity, and you take the charges to infinity, but as n squared. So you describe some kind of a parabola. Okay. And in that limit, is there an asymptotic match with this with the black hole entropy. Okay, so that's the question. And you can imagine why that's difficult. These calculations become time-consuming very fast. I'll show you a little bit later. And after, if somebody's interested in this in computer calculations, please ask me after the talk. It's a lot of fun. Just want to check one thing. Do you also see me when I'm waving my hands? Because sometimes I use it.
Yes.
Yes.
Okay, great, thanks. Okay. All right, so it's fun to sort of actually write this parabola and see what happens. Until n equal to 10 or so, you can do it in order to get some pattern. Okay, but that's a hard problem. There's another limit one can take, namely that you keep the theory fixed. Okay, you keep the rank fixed. So just one of these horizontal lines and just go infinitely far in that. This is easier to do, okay, both computationally as well as analytically. This, for obvious reasons, is called the Cardi-like limit. You fix the central charge and take high energy growth of states. Okay. And now, if you want to connect the black hole, you can do this first and then take the rank to infinity. Okay, so there is a regime of overlap. These two are completely different limits. There's one regime of overlap where everything is infinite. So the ratios are infinite and n is infinite, or in other words, charges are infinite, and then you take n to infinite. Okay, this is the regime. So here are some comments. So it captures very high energy states. The regime in which you connect with the black hole is when the black hole becomes infinitely large. So pictorially, it sort of fills up AdS space. So you write the gravitational solutions, and in the gravitational units, you take it to be very large. Okay. By the way, this is exactly what Strominger and Waffa had done in their pioneering work for flat space black holes. For flat space black holes, there is no AdS curvature. So the only thing you can play with is the size of the black hole. And they wrote asymptotic, they matched the black hole entropy asymptotically. Okay, so it's for an infinitely large black hole. So this is what we'll do today, sorry, in this lecture. And then in the fourth lecture, we'll take up the harder problem, the larger limit, which AdS allows you to even explore this problem. Okay, now if you want to write an asymptotic, if you want to write asymptotics of this form, you have to sort of be a little careful. Mathematically, there are two charges. Okay, so there's a double series, and asymptotics only makes sense, in one direction. Okay, so you have to give yourself some direction. Typically, you say n1 over n2 is fixed. Okay, because both are angular momentum plus our charge, so you want them to scale in the same way. And in the canonical ensemble, that means that sigma over tau is fixed. Today, I'll just discuss sigma equals tau. It can be generalized. So any questions about this? Okay. So then, we spent a lot of time in the first lecture translating the problem to the canonical ensemble because it's easier there. Things become linear and nicer. And the action also is a very simple rational function. And the question is, can you extract from this index? So now I've put sigma equals tau. It's only a function of tau. Can you extract from this index the black hole entropy? That's the canonical. I'm just mirroring the same question that I asked, the canonical ensemble. And the two limits that we talked about translate to this. Large n means that you hold tau fixed and you take n to infinity, whereas Cardi-like limit means you keep larger n fixed and tau goes to 0. Okay. So here where I sort of introduced tau goes to 0 a little fast, but at least intuitively that should be clear that when n goes to infinity, this if you're interested in the microcanonical objects, then that's dominated by the tau goes to 0 behavior. Okay. Any questions about this? All right. As we'll see, there's actually a bit of a subtlety here, which I'll discuss. Okay, so the first exercise we're going to do, so in all of this lecture, we'll stay in the Cardi-like limit. And the first exercise is do a saddle point calculation. Okay, remember that the entropy was the extremum of this action, which we know. So let's just do that extremization. So you have, this is the action, cubic divided by quadratic, and minus 2 pi n tau, and this is the minus 1 to the f and minus 1 to the n. Do the extremization, and you get such an equation. So if you differentiate this, you get this term. If you differentiate this, you get this term. Okay, there's an n square here that goes in the denominator, and I'll call this sort of gravitational charge, I'll call nu. Right? Is this you can some explicit algebraic equation for the saddle point, and as n tends to infinity, you can even eyeball what the solution is. So as n tends to infinity, it must be that tau goes to 0. Okay, if tau goes to 0, this is not there and that's not there. I have a feeling I missed a minus sign here. Okay, please check this. I'll just make a note to myself. Check sign. Okay, before I put it up, I'll check that. Okay, so anyway, so what you get is basically the numerator becomes 1 over and denominator is tau cube. So you get tau star, the saddle point, is 1 over nu to the 1/3. I'm pretty sure there's a minus sign, because what you get is you get that the tau star is a square root, cube root of 1 over nu. So that's what I've shown here. But now the cube root means that there's a choice of phase. Okay, one phase is that it's real. That cannot be, because tau, remember, has to live in the upper half plane. Okay, this is true both in gravity and in the field theory, both for the convergence of the partition function, as well as where the saddle point gravitational solution lives. The other solution is here, that's also not allowed. So essentially one of them is picked up. Okay, but this one that is picked up is a slight funny feature, that it's not that, which if you haven't played with this a lot, if you've just done the usual exercises in this story, the sort of path of rapid growth of the function, the saddle point, when you go along the saddle, is usually this. Okay, it's vertically on the axis. Here there's something funny. We're just going to keep this aside for the moment. We'll come back to this at the end of this lecture. Okay, this is sort of some second order effect that I want to discuss. Okay, but essentially tau goes to 0. So any questions about this? All right. Now there's a subtlety, which is the first order subtlety. Remember, in our map, the gravitational sigma and tau went to sigma plus 1 tau in the field theory. So as the charge becomes infinity, the gravitational sigma and tau go to 0. That means that the field theory sigma and tau go to -1, 0. Okay. When you put sigma equals tau, let me even just do that calculation very quickly. So that's the index. I'm going to take a pink pen. So what happens when you shift sigma to sigma plus 1? You get here plus 1/3. Okay. So this, remember, is the field theory index as a function of sigma. Now we want it as a function of sigma plus 1. That's what gravity asks you to calculate. You get a plus 1/3. And now if you put sigma equals tau, then you get 2 tau over 3. Okay. And therefore, that's the same as saying tau goes to tau minus 1, because the periodicity of this function in z goes to z plus 1, because everything is a function of e to the 2 pi z. Okay, so a quick calculation. You can convince yourself of that. That's not very difficult. There's nothing mysterious about that. Here we go. So in the limit that we're taking where sigma equals tau, this means that in the field theory, you should study tau goes to 1. All right. Was there a question?
Yeah, Samir, I wanted to ask a quick question. So you have two parameters, let's say tau and 1 over n, and you consider two limits. One goes to 0, another fixed, or another is fixed, and you go to 0. But in this quadrant, you can also approach the origin. Say you send tau to 0 and n to infinity at different rates. So these are different limits, and I wanted to ask if the two limits that you consider.
So by n, you mean the small n, right? Or are you?
Sorry, I talked about the capital N. So.
So in all, so as I said, so let me go back to this. Sorry.
Yes.
Let me just say something and then ask again. So here are the two limits you can study. Either, so first let's make it a one-dimensional problem. Is that an issue or not?
That's fine.
Okay, so let's imagine there's only one charge. Okay, small, yes, one charge.
Yes,
here, okay?
Yes.
So there are two limits. Either that the rank goes to infinity such that the gravitational charge is fixed. That's the black hole limit. Or the Cadillac limit, you fix the theory and take n to infinity.
Yes.
So this is the one I'm studying. Now, what is the question?
The question is, now imagine I take both to infinity with different rates.
You can do that. Okay, you can certainly do that. I've not thought about it. And then you have to ask, what kind of physics does it mean?
Exactly, yes. So in a sense, you're considering two limiting situations where one is much larger than the other, or other is much larger than the other, but...
No, sorry, stop. In this case, one is much larger than the other. Here, that's not the case. Here, both of them are scaling.
Yes, you're right, sorry, yes. Here, yes, okay.
That's the one which gravity asks you to do.
That's right.
All right, is that clear?
Yeah.
Okay, great, thanks. Okay, so here we are. So tau goes to 1. So that means that this saddle point, which is 1 over nu to the 1/3, let's ignore this phase for now, it's 1 over nu to the 1/3, becomes 1 plus 1 over nu to the 1/3. And sometimes this is called a complex saddle. Complex because in this way of thinking about it, I tau is usually the real parameter which you use to estimate the functions. And now you're not going to 0, but you're going to 1 here. Okay, that's what the field theory is saying. That's why it's called a complex saddle. Okay, so I times tau is not real but complex. Okay, so gravity somehow automatically forces you to do this. So let's now ask, what's the meaning of this complex saddle in CFT? Okay, so let me first do some, I just did some scribbling in the morning. So suppose, let me just change the subject a little bit, just as a warm up. Suppose you have some function of tau. Let's say it's 1 over eta of tau. Everybody has done this exercise, and you want to calculate the microcanonical degeneracy. Okay, you do this Fourier expansion, integral 0 to 1 f of tau e to the minus 2 pi n tau d tau. And then you know that you should focus near tau to 0, tau equal to 0, or at least that's what we are taught. And then near tau goes to 0, this is a modular form, so you can write down what the behavior is. And then this is 1. So essentially there's a 1 over tau behavior from the function at near tau goes to 0, exponential of 1 over tau, and that plays off against the linear piece in tau. You do a saddle point, you make an estimate, and you get some square root of n growth. Okay, I hope everybody is familiar with that. Okay, I'm going to assume that and maybe not say anything for a few seconds in case you want to ask a question about this. Okay, so this is say the theory of a free boson or just partition problem. Okay, we've seen this in many contexts. Okay, so this is how we're taught how to do it. But notice here, the tau is actually a complex number. Okay, so if you really want to do some Laplace method or something like that, okay, you have to ask yourself. So I mean, when n goes to the statement that when n goes to infinity, tau goes to 0, really should read that when n goes to infinity, imaginary tau goes to 0, because that's the thing that gives the damping. Okay, so let's do it in a slightly more sophisticated way as mathematicians do it, because it's very instructive. You think of right here, f of tau, write it as a function of q. Okay, so you write f of q as some dn q to dn, some q series of the sort, and then d of n is just the some inverse. So this is a contour integral you can do. This is the inverse Fourier transform that you had. Okay, and typically this function f in the q plane is essentially holomorphic in the unit disk, maybe except for the origin. Okay, that's not very important. But inside the unit disk, it's holomorphic. Okay, so this contour integral is completely well defined, and you can sort of wiggle this contour around as you want. Okay, and what we did in this sort of rough analysis means that you take the contour, tau goes to 0 means q goes to 1. So you take the contour, make it go close to q goes to 1. That's where the function looks singular. This was the singularity. Sorry, I even wrote it here, I think. There you go. This was the singularity that we all know very well because of modular transformation. And then basically you say that the whole integral is dominated from this region. Okay, and then this region you can use some Gaussian approximation and make it as an infinite integral, and that gives you, some Bessel function or two leading order. There you go. So you have something like this. To leading order, you get some square root of n. Okay, otherwise this thing is some Bessel function. Okay, and the saddle point here is so this you do by saddle point. You have 1 over tau in the exponent and tau. So when you play these off against each other, you get tau, is 1 over square root of n. And when you plug that back, you get square root of n, e to the square root of n as a growth. Okay. So this, I just repeated what we know in this with a slight change that I prefer to think of this function as a function of q. Okay. Now, one thing that's important in this discussion, which is implicit, okay, is the fact that over here for this function f, it's the dominant singularity. Okay. So in other words, typically what happens to this Q series is that inside the unit disk, they're all holomorphic except at the origin. And as Q goes to 1 in magnitude, at the edge of the unit disk, there are singularities. Okay, there's divergences. That's sort of obvious. It's a sum of A of n Q to the n. When Q becomes 1, there are divergences. Right? Now, the divergences often are at Q equal to 1, but not necessarily. There can be other divergences at other points along the unit disk. Okay, and the correct way to think about it, if you look at this contour prescription, is that you should look at the largest singularity, the dominant singularity, and that's the one where this function is estimated by. And in fact, if you do it for the eta function, you'll find that at every rational point, actually, there's a singularity. The q equal to 1 is the rational point in tau. I mean, okay, so when you go radially outward as e to the 2 pi I p over q, there's a singularity. Okay. And however, as I said, there are singularities in other places, and in the full, you can now do more. You can sort of estimate this, then you can bend the contour here and get some, contribution from that and so on. You actually get some infinite sum. So number theory, analytic number theorists sort of play with this a lot. This is called a Rademacher expansion, or this method was invented by Hardy and Ramanujan. It's called the circle method, and that's how you do it. Okay. So any questions about this? Okay. So now let's take another example where I define a function g, which is the function f, but with tau shifted by tau plus half to tau plus half. We call those Fourier coefficients dg. Now, by construction, it's totally obvious what's going to happen. G of tau is f of tau plus half. So in this graph, the thing that's going to happen to this graph is that it's going to rotate by a half. Everything rotates by half. Here I've drawn that. So I've shown the contour also rotated just to make the point. And therefore, it's obvious that the dominant singularity now is at -1. Okay. And so there might be a singularity here, but it's subdominant. And indeed, if you do the saddle point analysis, it's this saddle point which dominates the integral. Okay. It's not I over square root of n, but half plus I over square root of n. So instead of going here, now you have to go here. Okay. Now let's compare. So let's contrast f versus g. So from the definition, notice that because f is, so you just shift tau to tau plus half in the Fourier coefficient, it means that you pick up a factor of -1 to the n. So the coefficients, Fourier coefficients of g are just -1 to the f, Fourier coefficients of f. In magnitude, they're the same. They're just some overall phases. Now let's look at the saddle points. The imaginary parts of the saddle points are the same. The real parts of the saddle points are shifted exactly so as to absorb this oscillation of phase. Okay, and for G, the dominant growth is near the tau star of G. And if you look near the old saddle point, you'll make a mistake. You'll find a subdominant growth. Okay. So here's an exercise. This was suggested to me by Arash Ardehali, so thanks to him. So take, to really drive home this point, take f equals 1 over, so these are Jacobi theta functions. Take f equals 1 over theta 4 and g equals 1 over theta 3. Those are related by tau goes to tau plus half. And you'll see that as tau goes to 0, f is exponential of 1 over tau, and g does not have any growth at all. Okay, so sometimes there's subdominant growth, sometimes there's no growth. Okay, so that's a very nice exercise to work through. Okay, so now any questions about this? And now we're going to apply this to our problem. Very good. So let's go back to the superconformal index. So here I've already put tau equals sigma, and I'm going to call this function small gamma e. So this is this elliptic gamma function. And from the definition, it's clear that there is a periodicity in z goes to z plus 1, because in the infinite product, everything goes as e to the 2 pi I z. If z goes to z plus, because there's a periodicity in z goes to z plus 1, notice that here from this factor, it means that in tau, that the whole integral is periodic in tau goes to tau plus 3 because of the 1 over 3. If you missed yesterday, remember the 3 is appearing because of the R charge, the quantization of R charge of Yang-Mills theory, of n equal to 4 Yang-Mills theory. It's in units of 1/3. Okay, so the index is periodic in 3. And therefore, also notice that tau goes to, when we say tau goes to tau plus 1 over here, it's not obviously periodic. So that might have been confusing some of you. Okay, so tau goes to tau plus 3 is periodic. So tau equal to 0, 1, and minus 1 are actually different points for our system. All right. So now let's look at this function. Now, if you study this function, you'll find, okay, that at q goes to 1 as tau goes to 0, in fact, there is no growth. Okay. At tau goes to, so here I plotted it in the e to the 2 pi tau by 3 plane. Okay. So here there's no growth. Here is where the black hole lives. Tau goes to 1. And here there's another point which is interesting, which we'll talk about later. Okay. So that's the main story. If you want sort of one takeaway message, is this. So if you write everything in terms of e to the 2 pi tau, what you get is a triple cover of the complex plane. Okay, and these 3 points look to be on the same point. I mean, they project down to the same point, but in fact, in the covering space, they're different. Okay. Now, what we'll do now is, so since we want to study the black hole, we're going to zoom in on this point. Okay. So we're just going to change variables tau to tau plus 1 and call it tau goes to 0 just for convenience. Okay, any questions so far? Now what I'm going to do next is I'm just going to tell you the asymptotic estimates. So any questions about this sort of more philosophical side of the story? Okay. So let's do that. So in order to look at this, we need some estimates. So you want some asymptotic growth as tau goes to 0 of the functions. So again, so as I said, I forgot to put the references up last night. I'll certainly do it tonight. Okay. So these have been studied by mathematicians. In particular, there's a paper by Rains, which is interesting and gives you these estimates. Arash Ardehali has a nice paper where he summarizes this in a very readable manner, among other things. Okay, so these elliptic gamma functions, so typically the growth means you have exponential of some 1 over tau type of growth. For modular forms, you have exponential of 1 over tau. So log of the function goes to 1 over tau. These functions, it starts with 1 over tau square. Okay, so there's a 1 over tau square piece, 1 over tau piece, and then there's some O of 1 pieces, which I'm not writing. Okay, we're only interested in some leading growth. The coefficients are what are called periodic Bernoulli polynomials, which is, of course, a misnomer. You can't have a periodic polynomial. The definition is through either through a Fourier series of this type, or the reason they're called this is that when the argument is real and between 0 and 1, it's actually the Bernoulli polynomial, actually in the whole strip. Okay, and then you can just define the function by periodicity or by the Fourier expansion, which is the same. Okay, just to remind you, the first, so Bn is an nth order polynomial. Here is B2, and here is B3. Okay, B1 is X. So now we plug these estimates into our function. I should tell you what Z is here. So this part, so this was the function we derived yesterday. Remember, this came from the vector multiplets. I'll call Z vec, and this one is from the 3 chiral multiplets. It's Z chi. So you plug this in, and what you find is that, again, there is some 1 over tau square piece, 1 over tau piece, and now the coefficients are functions of the gauge holonomies and the differences. Okay, they're essentially these B3s and B2s summed over the whole matrix. Okay. All right. Yeah, so there's a small, there's a small subtlety that the Z-vec, if this estimate, if you apply it for r equal to 0 or 2, like you need for the vector multiplet, it actually strictly applies only when tau is not equal to 0. I mean, what I mean is you have to sort of cut out a little piece and then make the estimate, but then there's some uniform convergence properties. So everything is okay. This is some technical part I don't want to get into unless somebody's really keen on this, please ask me later. Okay, everything works, is the point. So it's a completely minor thing. Okay, so now let's look at the leading behavior. The leading behavior is like 1 over tau square times this function, what I call V2, which is a piecewise cubic polynomial. Here I plotted it, not very well. It looks like that. And it's clear that the minimum here is at x equal to 0. Okay. And so now you want to do saddle point. So the saddle point, the parameter for the saddle point here is only tau. Okay, so I'm fixing the rank. I take tau goes to 0, and then I get this behavior, and then the saddle sits here. Okay. So at the saddle point value, Uij is 0. And when you evaluate the potentials, you'll find some n square behavior. You put that all back, you find that this is log of in grows as this. So you have n square here times 1 over tau square, 1 over tau, and O of 1. And it's a trivial exercise to check. This is exactly the I black hole up to this order.
Sorry, I'm a bit confused about the previous slide.
Yeah.
So you said it's a cubic. Yes. Okay.
So just one second.
Right. Yeah.
Yes. Please.
Well, it's a kind of stupid question, but like you said, it's a cubic polynomial, but the plot didn't look like cubic.
Yeah, so it's piecewise. So these things. So sorry, it's piecewise here. So these are special points. This. Sorry, I forgot to say. This is also a special point. You have to sew it together.
Okay.
Okay. I mean, so it's 0 to 1 is where it's cubic. Here, this is where it's cubic. So if you look at my Bernoulli function, here it is. Okay, so it's defined like this. And then you make it periodic. Okay. Very good. Any other questions? Okay, so this is how you recover. So you completely recover the black hole. Sorry, was there a question?
Yeah, sorry, Samir, could you maybe explain a little bit more? So there's a saddle point where the eigenvalues are all clamped together at some point on the circle?
Yes, thank you. Sorry, in fact, I had it in mind to say. I forgot to say. So the saddle point value is Uij equal to 0. Now, in fact, if you take the original index and just put ui equals uj, let's say you put all of them at 0 or some constant value, you get actually that the index is 0. Okay, let's look at that. It is, no, I want the infinite product. Here's the infinite product, but maybe I'll go back to the beginning here. Okay, suppose I put here uij in this integrand. Suppose I put uij equal to 0. Okay, and I take tau to 0. You'll see that there's a 0 of this elliptic gamma function. Okay, the whole index actually vanishes. Okay, so that's a little bit subtle, and that's so sorry. If you looked here, that all the 0. Sorry for moving back and forth. The 0 is coming purely from the vector multiplet. It's the chiral multiplets are perfectly fine even if you put uij equal to 0. Okay, so sorry, let me say it again. So take a fixed tau and sigma, okay, and then put uij equal to 0. Okay, then you find that the whole index vanishes, and the 0 comes from this part of the function. Okay, and that's exactly this technical comment that I mentioned, namely the vector multiplet there's a small issue. And what you have to do is it's a question of order of limits. Here we go. That actually you have to sort of stay away from uij equal to 0. Sorry, I know what is confusing. Confusing because I said something wrong. Okay, now my pen stopped working again. Here we go. There. Ah, u equals 0, I meant. So what uij mean, the z. Okay, so actually what you have to do is, let me take another color, is so if the estimates are valid like this, you first take some epsilon cutoff. Okay, you make the estimate and all the eigenvalues will sort of bunch up here. The differences will bunch up here, and that's perfectly legit. And then you can estimate the integral and then take the cutoff to 0. Okay, that's what is meant by this uniform convergence. Okay, is that more or less clear? Was that the question?
Yeah, okay, thank you.
Okay, so from your response, it felt like maybe it was not too clear. I'll explain this again during the chat. Okay. All right. What happened? Okay, there we go. Okay. All right. Now we want to generalize this to an arbitrary n equal to 1 superconform field theory. Okay, with Lagrangian description. So what happens? So there's an explicit integral representation. Like yesterday, I hinted about this. So instead of ui minus uj, you have some sum over representations. So that's one difference. And here, instead of 1/3, you'll get r charge over 2. Okay. So you repeat the same process. You can write these asymptotic estimates. You'll find some sum over multiplets of this sort. Okay. And then these sum over multiplets will be some chirals, and then this part from the vectors, and the sum will be essentially dimensions of the representations times r minus 1 and r minus 1 cube. Okay. Then those things sum to trace r and trace r cube. Okay. Then you use anomaly cancellation and use this definition of the A and C central charges, which are linear combinations of trace r and trace r cube. Okay, and what you find is you can write the whole thing in terms of the A and C anomaly coefficients. Okay, so log in is again, so this there's a 1 plus 3 sigma plus 3 tau divided by sigma tau times 3c minus 2a, and then there is so this is like 1 over, the leading term is like 1 over sigma tau quadratic. And there's some 1 over sigma 1 over tau terms, more 1 over sigma 1 over tau terms. These you don't see in supergravity when A equal to C. So this is some higher derivative effect in supergravity. And this agrees completely at this order with the gravitational action. Okay. So that was the general result. I didn't derive this for you, but this is in the papers. Okay, so we have done is to recover the on-shell action of the AdS 5 black hole from the superconform field theory in the canonical ensemble. We just did that in this Cardy-like limit. Okay, and the microcanonical entropy, as we already saw, follows from the Legendre transform. Okay, so any questions about this?
So can you reproduce also this A minus C term from gravity?
Can I repeat what?
Can you reproduce, you mentioned this A minus C term coming from
I haven't been, no, so this hasn't been done yet, but A minus C typically is some Chern-Simons term, and it couples to, A minus C is an anomaly coefficient, so in AdS 5 will couple to some A wedge R term. So for n equal to 4 Yang-Mills, it's not there, but if you do n equal to 1 theories, so if you remember the Lagrangian of minimal supergravity that I presented, there was this Chern-Simons coupling for the gauge field. If you write it at higher derivative level, there's also Chern-Simons coupling for the gravitational, for the spin connection. That's where it should come from. I have not done, I think nobody's done the calculation. That'll be nice to do.
Thanks.
See, these kind of calculations, by the way, have been done in flat space and they work perfectly fine. That's where my intuition is coming from. I know that in flat space, I've done such calculations for higher derivatives, and that precisely reproduce these kinds of terms. In the context of AdS 3, for instance, this is like some other gravitational anomaly, C minus C tilde or something. Shota-san, you have a question?
Yes, yeah. So in the case of it, eta function, you said like there are infinitely many singularities. And here you said like there are 3 singularities. Are they all the singularities, or there are
so
more?
I didn't say there are only 3. I said there are 3. Thank you very much. That's where I'm heading. Okay, so just give me 5 minutes. Let me finish this lecture and then ask me this question.
Okay, thanks.
So it's a fantastic question. Okay, so let's, so this, I mean, this would have been, for instance, a stopping point. You could have sort of declared the problem solved here, okay? That we managed to do what we set out to do, at least in this very large infinite charge limit, okay? Very good. Any other questions? I'm happy to wait for a bit. Either looking forward or about what I said. Yeah, maybe I'll say this thing about the saddle point estimate again, which Kyriakos asked about. The idea is, so you have some integral. Yeah. Sorry?
The question I was asking before is, there were 2 integrals, right? I mean, there were the integrals over the holonomies and the integral over tau, right? Over Q.
Sorry, holonomies and?
And you had an integral over Q also, right?
I didn't hear. Integral over what? Q.
Q.
No. I've not done that yet. So right now, my goal, so sorry, let me go back. So here I was asking, what is the meaning of the complex saddle? And I was telling you in the context of microcanonical versus canonical, that this complex saddle just means that there's some oscillation of phases in the microcanonical ensemble. For that, I had to do an integral over Q or tau. Okay, leave that aside for the moment. And first, let's just derive. So that was an explanation of why we should look near tau goes to 1 and not tau goes to 0. I gave you some simple example of why that is the case. Okay, and having said that, I didn't look at the microcanonical degeneracy of our problem yet. That's where I'm headed. All I did was take this and I just estimated this U integral using the saddle point. So I fixed tau, and the answer is I get a canonical answer, and that agrees with the on-shell action of the black hole.
Okay, thank you.
So please tell me your question.
No, this part is clear. Thank you.
Okay, this part is clear. Okay, so the U integral about, I thought you were worried about the technical. The technical part is a technical part. It can be solved. It's perfectly rigorous. Okay, you do a saddle point analysis, and there's an order of limits you have to do. So you have to first estimate the function, and then use that estimate, do the integral, and then take any limits you need. Okay, so that part is absolutely clear. But the more fun part comes now. Okay, so maybe this is what you're asking. So we've recovered the on-shell action in the canonical ensemble, and the microcanonical entropy should follow from the Legendre transform. Okay, so let's look at a plot of the Legendre transform. Okay, so I did some computer calculations, and here they are. So what I've plotted is the black hole entropy. Those are the solid curves. Okay, versus the log of the absolute value of the degeneracy. Okay. Yeah, when I showed this to my, some mathematician friends, they almost killed me because the absolute value is a terrible thing to do. But let's just do that. Okay. I'll tell you what happens to the degeneracy itself after some time. Okay. Let's just think about the physics and see, do we capture the black hole entropy here? Okay. And you see a few things in this plot. So I went from n equal to 2 to n equal to 10. And then my computer ran out of steam. And here's what you see. Okay, there are some 3 patterns, a few patterns. So the first thing to note is the fact that it essentially works. Okay, the black hole entropy is essentially the microcanonical degeneracies essentially follow the black hole entropy. Okay, so before trying to solve this problem analytically, if you'd just done that, if you'd just taken this matrix integral, put in a computer and ask whether it agrees, you'll see even for very low charges it agrees. Okay. Then you see that, well, there are many features to this. You see that it doesn't quite agree. Okay, that not agreement comes from various factors. Essentially, these are higher order effects. Okay, there's a small logarithmic effect that you see here, and that effect tends to go away as, and there's also a small 1/n effect. So that effect tends to go away as n becomes large. You see that. Okay, for n equal to 2, it's pronounced, and here already you see it's less, and here it's less. Okay, so let's ignore that. I don't want to discuss this today. Then you see the following fact that, in fact, if you zoom in, let's zoom in. Okay, you see that there are actually oscillations. Okay, there's a clear pattern of oscillations, and at n equal to 10, it's absolutely clear. Okay, around this value that you want. And finally, you see that the oscillations start after some time. So there's a bit of a gap. Okay, it's very small here, here it's very pronounced. There's a bit of a gap where something else happens, then the oscillation starts. Okay, and I should say one more thing, that if instead, let me say that later. Okay, so let's first focus on this. What time is this? So maybe I'll say one more thing before even looking at that plot. This is essentially what Kyriakos was asking. Okay, if you before plotting log of absolute value of n, okay, so suppose you just plot d of n itself. Okay, this is terrible to plot because it has exponential growth. So let's divide this by e to the s black hole. Okay, so at least you get some reasonable plot. Okay, when you do this, what you find is something like this. I should have showed this, I should have done this, but it was up till late last night and forgot. So what you get is something like this. So suppose you plot this on the y-axis, okay, versus n. All right. What you find is something like this. Okay, it's completely nonsensical. You don't see any pattern. Okay. But one thing you see is that you see that it's, sorry, red is a bad color. I don't know if you can see this, I'll use pink. What you see is that it's all inside, roughly inside 0 to 1. Okay, there's a -1 and 1. Okay, so that means that your basic estimate is correct. Okay, but the phases have gone for a toss. Okay, you see like a scatter plot, but all between 0 and 1. So that means that your basic estimate is correct, right? In magnitude, it's still correct. Then you can do one thing, namely you shift the phases. So instead of e to the s black hole of n, if you do d of n divided by e to the s black hole of n times e to the 2 pi I n over 3. Okay, this is the analog of the oscillation that I showed you in this simple example of f and g. Okay, this e to the 2 pi n over 3 we saw in many of the formulas. If you plot this, and then you see, already the thing simplifies a lot, enormously. What you see is again between 0 and 1, well, -1 and 1. Okay, but it's much better. You see something like that. You see 3 curves of that type. Okay, so that means that this has completely solved this problem. The oscillation problem was essentially what was throwing you off. So this is exactly what this tau goes to tau plus 1 is. Okay, in the microcanonical picture, this is how you discover it. Okay. Kyriakos, is this what you were asking, more or less?
Yeah, thank you. So can I ask something now related to this? So from this point of view, is it clear why in the original computation of the index, I mean, if the chemical potential is real, why you get such a small answer? I mean,
yeah, absolutely. So I thought
is this cancellation is the cancellation so perfect that these very big numbers, you know, give you something about the one?
Absolutely. So I urge you to do this exercise, this simple exercise in Jacobi theta functions. Okay, you have 1 over theta that grows mildly exponentially. It's like 1 over tau. It grows. It has a square root of n growth. Okay, and there's oscillations -1 to the n oscillations. Okay, 1 over theta 3 has just all positive numbers, and this one has positive negative. Okay, and if you estimate it at the wrong point, namely here near 0, you get no growth at all, and the reason is because the oscillations, it's exactly 1 and so the things grow, but exactly with opposite signs. So if you try to do a saddle point estimate, they just sum up to 0. At large n, it's exactly 0. It's exactly what is going on here. So here there are those 3 things, they will all add up to 0. So this is the original calculation. Yeah. Okay. Yes. Thank you. Okay. So now let me go back to what I was saying. Okay. So that's sort of the 0th order problem, which this lecture was supposed to sort of explain. Now let's look at some interesting features. So I said there are many features. Okay. So firstly, that it agrees. Now I go back to log of absolute value, and now there's this oscillation, and there is this near sort of very small charge behavior. Okay. Let's explain the oscillation. The oscillation happens because of this, what I call a second order effect. The fact that you're not, so the first order effect was that instead of going to 0, you go to 1. Okay. So you shouldn't go there, you should go here in these shifted variables. Now the second order effect happens because you're not actually going like this vertically, you're going with a little bit of an angle because of this phase. And if you calculate at the saddle point, we already did the saddle point evaluation. If you calculate the value of the partition function at the saddle point, so now I put n instead of tau because it's the same thing at the saddle point, you find that there's an exponential growth like the black hole, and there is a phase which, so the imaginary part of the action is not 0. If it were 0, you would have got precisely the black hole. Okay, this is not a rapid oscillation. Okay, the rapid oscillation we've already taken care of by shifting tau properly. Okay, what this is the fact that we only focused here in doing this saddle point estimate, and in fact there is another saddle of this system which is sitting here. So this was tau equals to 1, so this is tau equals -1. So e to the 2 pi I by 3 and e to the minus 2 pi I by 3. Okay, it's like a complex conjugate saddle. Okay, you would have never seen this in the Cardy limit. That I want to emphasize because there's been some confusion in the literature. Okay, the Cardy limit focuses on one point. You can also focus on this. It looks very similar technically. It's a different saddle point. Okay, maybe a better word instead of complex. I mean, it is complex, but sort of in physics, maybe we should call this parity conjugate. Parity conjugate, because that's what it really is. Okay, the original theory has a certain parity symmetry, and that's broken by the angular momentum. But in fact, if you zoom in at one point, but if you look at the whole theory, it's restored. That's the parity I'm talking about, and that restored by the fact that there's another saddle point. Okay. So I hope that is clear. Yeah, so what I just said is sort of implicit in many papers, but the story is extremely clear. So you have, so what happens when you add these two saddles is that you get e to the real part of the entropy. So e to the plus I imaginary plus e to the minus I imaginary. So you get some cosine, and that's exactly this oscillation that I showed you in the microcanonical leech analysis. All right. So what I'm saying is, if you do the saddle point analysis and include both the saddles, the analytic estimate is this. You get e to the s black hole times a cosine, okay, times a small rapid oscillation, which I've already factored out. And this precisely gives you, this you can check on the nose, agrees with if you just actually plot d of n. Okay, these are these oscillations that are. Okay, so the three patterns are as follows. Again, to repeat, one is there's an overall growth. There's a rapid oscillation. When you understand that, you keep factoring that out, and then there is this macroscopic oscillation. Okay, the sort of time scale for this is n squared. It's as big as the black hole. Okay, that's the end of this seminar. But this talk, I mean this lecture. Since Shota-san already asked this question, we said now that there are three saddles, and I didn't tell you very much about this function. I said there are three saddles here. There's no growth, and these two have equal growth with opposite phases. Okay, I just told you. So the natural question is: are there other saddles, just like the eta function 1 over the eta function? Okay, recall that if there are other saddles, you have to expand the whole thing in terms of all saddles, and that's what I want to pick up on in the next talk. So shall we take a small break now?
Yeah, maybe, are there any questions?
Can I ask one?
Please.
So is it possible to reproduce the imaginary part from gravity?
So, yeah, that's a good question. Let me show something here. The answer is yes, if you're careful, but then you have to be really careful. So here, if you notice, this was supposed to be, this is the Cardilhac. So forget the Cardilhac limit. Let's just do a saddle point analysis at large n, for instance. Okay. So suppose you want some large n analysis, and you take the charges also to scale as n. Okay. So then you can do a large n analysis. Then notice that in this way of writing it, I also included this phase. This phase appears because of the constraint that we had. When you wrote the constraint in gravity of this third chemical potential in terms of the first two, you also get this extra phase like so. And this is what then is interpreted as minus 1 to the f. Yesterday we went to the story. Right? So this is both from gravity and from field theory. See it? And when you put this in, so there's also an n square here. Okay, an n square here. When you do a saddle point analysis, you do see a phase. But I sort of emphasize that in order to see that, you have to keep track of all the background chemical potentials, the background supergravity, R-symmetric H fields, and so on. If you do that, you can do it. So in our 1810 paper, what we did is that we found such a phase, and we didn't like it because this is not good. So we said, well, let's just impose that this phase is real. This exponent is real. If you do that, we got on the nose the black hole entropy. But in fact, you shouldn't throw away the phase. The phase is there both in gravity and in field theory. Okay, and if you set that to 0, you get the entropy on the nose. That calculation still stays, but the phases also can be matched. Okay, so what does it mean? The phase appears in gravity because you're studying in gravity, what you study is something like this. So you get a phase, and it's not a real object. But in fact, if you would study the full quantum gravity partition function, you'll get not an imaginary part of the action, but you'll get a real oscillation of this type. Okay, that's what you're supposed to do in quantum gravity. You sum over all saddles. There is this black hole saddle, and there's this conjugate saddle. And if you put them together, there is this macroscopic oscillation. You can ask what is the meaning of this saddle in gravity. We'll come to that in the next talk.
Are there any
answer your question, more or less?
Yes, Samir, I've got a question.
Yeah,
is it the right time to ask?
Did I answer your question, more or less? Okay, maybe it's not there. Abhiram, please.
Yeah, so is it the right time to ask about these modular hints of the super conformal index, or
not yet?
Not yet. Okay. I had one more
I'll
question.
tell you, I'll keep you in mind.
Okay, I actually have one more question. So you mentioned the Rademacher circle method that you were going to use to compute the SCFT for Fourier coefficients.
No, I didn't say that. I didn't say I'm going to use that. I said that it's well known how it happens for modular forms.
I see. Okay.
Yeah.
Okay. Good. Okay. Sorry.
There is, so remember, I mean, since you brought this up, when you estimate Fourier coefficient of modular forms, you do the circle method. That's just complex analysis, like this.
Right. Yeah.
But to the difference, so this is what Hardy and Ramanujan did. Okay. But many, like this was in the early 1900s. In 1960 or so, Rademacher was sort of giving a lecture about it, and he tried to rewrite it. And he realized by rearranging the error terms in that estimate, and crucially using the modular transformation property, he could make a convergent series. Okay, that's a very difficult thing. And in general, we don't expect anything of the sort in Q series. But generically, Q series always have this kind of thing. There are lots of singularities as Q goes to 1 in magnitude on the unit disk, and then you have to estimate all of them.
Right.
Professor Murthy?
Yes, please.
Actually, why we need to study this saddle point, or under what condition, why we need to study the saddle point?
Okay, so let's go back here. Oops. Let's go back to the beginning. Here we go. Remember, the basic question we want to ask is the black hole degeneracy, black hole entropy, is that contained in this degeneracy? Okay. What does that mean? It means that for every n, you should be able to calculate this. But for every n, the black hole is not even well defined. If n is very small, then you're in some quantum gravitational regime. We don't know how to do such things. So the black hole automatically tells you that you must have some scaling of charges. Okay. And therefore, the correct mathematical way to phrase this is there an asymptotic growth of states which equals this asymptotic growth of states? Asymptotic means that you start with some saddle point and then you ask for corrections. Okay, and then there are two possible asymptotic estimates we can make. One is this large n, and one is this Cardillat limit. Okay, we don't, in some sense, this is the best we know how to do. Okay, you start with either charge equal to infinity or rank equal to infinity. Ask for the saddle point. That's the analysis. So as I said, if you want to do a finite end calculation, it's very, very difficult. So these are some analytic methods that have been developed by physicists and mathematicians over the last 100 years. You want to use that.
Is there any other questions?
Samir, you have shown that there are enough 1/16 PPS states in the theory to reproduce black hole entropy.
Yes.
Is this the right moment to make some comments about previous works where it was argued that only supergravity is?
Go ahead.
No, I mean there were some previous works.
Oh, you want me to make comments? No, I will make comments at the end of the next hour.
Okay.
So are there any more questions?
So I hope I will get one more hour because I need one more hour.
Yes.
Yeah. Because there were questions after my talk, right? Yeah.
You can go ahead, please.
So can I just want some water because I finished my water. I'm just going to take a 2-minute break. Is that all right?
Yeah.
We can make them a 5-minute break, or
okay, as you want. Yeah. So I'll just maybe I'll stop sharing.
Yeah, we can have a 5 minutes break so that you can.
Okay, fine. I just want some water. That's all.